Okay, let's start. Good afternoon, everyone. Thank you very much for joining us today in our cycle of seminars of the Astronomy Department. Today I am very glad to introduce Lucas Barreto Mota, who is going to give the seminar today. Lucas has his bachelor degree in physics from IFUSP and a master degree from IAG, and during which he visited the Center for Computational Astrophysics in the Flatiron Institute of New York. And currently he's finishing his PhD here at IAG. He also made a sandwich stay at the University of Wisconsin-Madison, also in the US. So Lucas, whenever you're ready, you can start.
Thank you, everyone. Can you guys hear me well? So thank you very much for this the opportunity to talk here today. I'll be talking a little bit about the work I've been doing in IAG since my master's, and this is pretty much the summary of it. Like, we started with molecular clouds, and now we are working with high energy cosmic rays. I'll be dividing the talk pretty much in two parts. First, I will be talking about the work in my master's degree, magnetic field orientation, self-gravitating turbulent molecular clouds. So more towards the ISM in general, structure formation, and then the second part we'll be discussing more towards cosmic rays, high energy cosmic rays. So let's start with the turbulence, magnetic fields, and molecular clouds. So we were interested in understanding the observations made by Planck at the time. So Planck observed the entire sky. In particular, it made several observations in these marked molecular clouds over here. And it's these regions are very interesting. They are because they are the birthplace of stars. They have this presence of filamentary structures. They are pretty extent, up to 100 parsecs. These clouds in particular have this range of distance from our planet, and they are very low temperature, but still they are very, very turbulent. So we see the formation of several structures in these places. So what is interesting in looking at these structures? So when we think about the ingredients that we have in these clouds, the main ingredients are the gas, dust, magnetic fields, and the cosmic rays. These and magnetic fields, we can think about it that they are not neutral. We have ions in there. We have electrons, protons there. Well, which means that these gas will be affected by the magnetic fields. However, if we think a region large enough, the total charge in the region will be neutral, but we cannot discard this interaction of the magnetic fields. So above a certain distance that we call the bi-length, we can ignore that we have charges there, but we cannot ignore their effects. So what is interesting is then that the magnetic fields will affect the plasma, and the plasma will affect back the magnetic fields, and we need to understand this interaction. And what is interesting about the dust is that the fact that that the dust is there, it allows us a way to identify the direction of these magnetic fields through polarization. So the dust will absorb part of the light, part will come to Earth, or even like due to the grains are not being rounded, they have like a certain axis that will be a little bit bigger than the other, and this allows us to use the light to identify the magnetic fields. And here is an example of a molecular cloud Taurus observed by Planck, and these lines here, as you can see, are the projected magnetic field in the sky, and you can see that we have structures less dense aligned at the same time that we have these dense regions perpendicular to the field. So how can we understand that? So first we need to think a little bit about turbulence. Turbulence is a process that we have everywhere in the universe. We can see in the atmosphere, we can see in the largest scales of the galaxy. And a lot of the time you will see structures like we see that in the plane, especially in Jupiter there, we see these vortices. So when we study turbulence, we can think about turbulence as this power law, and where we have these large vortices as at the large scales, where the energy is being injected, and this energy will cascade down towards smaller scales, usually following this law of 5/3, which we call Kolmogorov. And oh, sorry, there should be a minus here. I forgot the minus. Really sorry about that. And then, but still, we'll have this this power law that should be a minus there, and then we have this superposition of these vortices all the way down to the viscous scale, where this turbulence is dissipated in the smallest scales and becomes laminar. But as I just told you, the fluid will be affected by the magnetic fields, and there will be a difference in this cascading when we have the magnetic field, and then we'll have this law over here that differentiates along and perpendicular to the field, and it will be elongated along the magnetic field line because of this effect. But and it's interesting that when we look at the sky, we see this power law going all the way from the fluctuations in the ISM all the way to the neighborhood of our solar system. And while we're doing this turbulence, talking about turbulence, I want you guys to remember, I'll come back to these numbers, but like think that we can inject a lot of energy at once in the system, and this system can become what we call it supersonic. So what that means, if this turbulence velocity is larger than the sound speed of the media, we can start to have compressions and shocks in there, and this will be, of course, important to forming stars later on. But at the same time, since we have the magnetic field, we have another velocity, a characteristic velocity that we call the Alfvén speed, which is a measure of how strong we can see it as a measure of how strong the magnetic field is. There is more to it. It's related to the waves traveling through the plasma, but I won't go too far into that right now. Just think that whenever we have a supersonic system, we can have shocks, and if the system is super-Alfvénic or Sub-Alfvénic, or in other words, if MA is larger than 1 or smaller than 1, it's a way to measure the magnetic field. So if it's larger, the magnetic field shouldn't be too important. If it's smaller than 1, then the field should play a big role in the turbulence. So how do we relate then turbulence to these collapsing structures that are forming in the ISM? One way to do that is looking directly to the density distribution. And then there's this characteristic curve that shows up when we have just turbulence, which is a log normal distribution for the density. But what is interesting is that as the structures collapse and we have this coagulation of matter at denser regions, and these regions start to become important, a second part of the curve shows up, and we start to have this power law at larger densities that we can use to correlate how much of the structures are being affected by gravity. And then we can then define a certain critical role above which we have these structures affected by gravity. So okay, we want to measure how the structures are aligned or not to the magnetic field, correct? So one way of doing this, we can look at the gradients of density and the column density if we look at the observations of Planck, for instance. And then what we can do is measure the angle between the magnetic field or the projected field that we can get from polarization. And then we can measure this and create a histogram at different density thresholds. And then what we have here, for instance, is one of these examples. So the light blue here represent like structures that are more aligned to the field. So at that density range, we will have if we have a peak near 0 cosine equals 0, we have these structures aligned. If we have a peak in the wings, means that the structures at that density range are perpendicular to the magnetic field. So we can go a bit further with that, and we can actually build a statistical method that summarize those histograms into one number. That's the projected Rayleigh statistics. So the idea here is, again, looking at this gradient of density, column density. So here, imagine that you have the structure here. The gradient will always be perpendicular to the ISO contour that we have. So we can use this characteristic to compare to the magnetic field. Or, for instance, in the case of the column density, with this E here will be the polarization vector. And then we can do this sum over here in the right. And this will give us a number that, well, when it's above 0, will tell us that the structures are aligned to the field at that density, mostly aligned. Or if it's below 0, means that at that density range, it will be mostly perpendicular. Okay, so how do we calculate the polarization then in our simulations? Well, in our simulations, we actually have all the information of the gas, of the magnetic field. So we can assume a few things about the gas there. We assume that only the dust is emitting. We can assume that they are perfectly aligned, which means actually that the dust is completely perpendicular to the field, not aligned along the field, because the grains are actually spinning quite fast there. So they end up aligning perpendicular to the field. So the light, the infrared light that it would emit, it will actually be polarized perpendicular to the field, and you can estimate with that angle using calculate the Stokes parameters in each cell, sum these along the line of sight that we are considering, and we have a projected estimation of the magnetic field in our mock-up observation. So, and then we can then estimate this polarization there. So now going to what the work we did, we built 2 families of simulations. One isothermal, considering only the presence of MHD turbulence, and with no self-gravity, and another one, an isothermal model, same thing, but then considering the self-gravity. Sorry, thank you. Yeah, that will allow the star formation. So it is an essential ingredient that we have to consider. Otherwise, well, we wouldn't have stars, right? So these are pretty much the equations we are using. The only difference here, it will be that the gravity terms in one of them will not be there. So this is one of the examples of these simulations. So you can see that the system starts only with the injection of turbulence. Turbulence will start to form over densities. So you can see these blue regions, and at the end, it will collapse and form like these filamentaries and dense regions. And as I told you, I was coming back to this. So in our simulations, we considered a highly supersonic. In these examples that I will be showing here, all the MS for them is 7, so highly supersonic. But we'll consider 2 cases for MA. So one MA equals 2 and 1.5. The idea being, of course, like the magnetic field will be really important to the dynamic of the glass. The other, not so much. And yeah, all the blocks are periodic, so with this size here, so you can imagine more or less a 10 parsec region in the sky. And okay, so what do we see in the Sub-Alfvénic case here? This is the 3D view of the beginning. You see that we have already a lot of structures formed, but once it collapses, we have this enhancement, but the field continues more or less all parallel to the initial direction. But when we go to the super-Alfvénic, we have the same thing, but now the field is completely distorted. We lose all this initial behavior that we had. And well, if we look then to the evolution of the density, we can see that the dense regions are collapsing. We start to have the the formation of the power law, we follow it up all the way to when it reaches about 1.5, which is like the limit, more or less, that for our simulations when we could follow the formation of the sinkholes. Since we do not really add sinkholes, this was kind of the limit of the resolution that we could follow. But still, we see that the gravity is already important there. Another important thing that another interesting thing that we can look at is the density power spectrum, and it begins with the k2 minus 5/3. Now it's right, and so at the beginning it follows more or less the Kolmogorov, but as it collapses, the contribution of these dense regions starts to flat out, and because we have this concentration of mass, so we definitely have the gravity working in these dense regions. And well, if we then calculate the histograms of relative orientation, we can see that this is with turbulence only. So you can see that above it's the supersonic Sub-Alfvénic. So you can see so this is the one above is the magnetic field is important, below not so much. And we can see that as it collapses for the dense regions, which is these purple histograms here, we have this the wings start to rise, which means that we have this concentration of perpendicular structures, which is still present in the super-Alfvénic. So even if the magnetic field is not strong at the beginning, at the end with the collapse, it will become important, especially in the denser regions. We can also so in what we see then in the column density. So more or less the same. But now, since we are integrating, we are losing a lot of this direction in information in the super-Alfvénic, and the Sub-Alfvénic we actually will have a dependence. It depends on how the mean magnetic field in the cloud is. And then so just to I'll show 2 slides next. So from left to right, what I did is the initial to consider a line of sight one perpendicular to the initial average B. So initially the B is along Z, and as we go to the right here, we get like 45-degree angle, and the other one it's completely parallel to the initial magnetic field. And if we look then to the column density maps, and you do the PRS estimation. So remember, from positive to negative, it goes from parallel to perpendicular. So as we go to higher densities, column densities, we see this transition from parallel to perpendicular. But if the line of sight is parallel to the initial magnetic field, we lose this information. And if you look here, I'll show in the next slide, parallel to the initial magnetic field, it kind of looks like the same as if the magnetic field wasn't important in that system, if it wasn't Sub-Alfvénic. But if we look at the PRS, in this case, it is mostly positive. And however, we do see that there is a small hint here that it's a bit smaller at higher densities. So let's compare this then to the observations and what we see. So here's like the final evolution of these 2 simulations here, Sub-Alfvénic and super-Alfvénic. And down here is that same Taurus filament, and you can see here the magnetic field from the polarization is showed here, and we can see that we have this large structure perpendicular to the field, and we have several filaments with less density falling down, mostly parallel to this estimated magnetic field there. And what is interesting then is that if we look at this PRS for these distributions, it seems more compatible with the Sub-Alfvénic, so the magnetic field should be important in these regions. But even if it's not, even in the super-Alfvénic case, we still see that there are some similarities there that that kind of comparable to what we have in these molecular clouds here. So you can see here it's the PRS from which clouds they were calculated. So summarizing then our findings in this first part, our simulations show that the densest regions of the molecular clouds are perpendicular to the magnetic field. Gravity enhances this formation of structures perpendicular, especially at the higher densities. And this, in the end, it doesn't matter if the field is strong or not. At some point, you end up accumulating enough, and it becomes important. But our results seem to point towards a dominance of sub-Alfvénic turbulence in these regions. So now let's change a little bit the pace of the things, and let's go to the highest energies and how they interact with these kind of regions. So nowadays, in the last few years, we have had several exciting observations coming from these the current generation of high energy observatories. Here are a few of them. One of the more exciting, let's say, more recent observations has been LHAASO, that is down here. This is located in China. And this is a large field with a lot of Cherenkov tanks that can stay there, collecting a lot of cosmic rays that come from the sky, and gamma rays. Sorry. And what is really interesting, this is the observations made by LHAASO in the range of 1 to 25 TeV. So, and you can see that it has this telescope has a lot of sensitivity, but it doesn't have a lot of resolution. Still, as you can see, we have a lot of gamma rays coming from our galaxy, and we do not quite understand these regions yet. And this is what it's so exciting from these observations, that we have a lot to discover still in this high energy range of energies. So here, so what we see several photons coming from very extended sources. So above here is a young massive stellar cluster, a very massive region called W43 observed by LHAASO. Down here is two pulsar ring nebulas observed by Hawk. And as you can see, I don't know if you guys can see down in the bottom here, there's a small ball over here. This is the moon. So this is like the proportional to the sky. So you can see this is massive, and but we do not quite understand. And these observations are part of a search for what we call PeVatrons. So when we think about the energies we have from CERN, we reach up to 10 to 14 electron volts. These sources here can go up to 10 to 17. So this is the limit we can accelerate inside our galaxy. But when we look these regions and we start to calculate how much time we need to spend, the cosmic rays need to spend around the sources to understand this emission, we reach that we should have a diffusion coefficient of this value or less. The problem is this is like 2 orders of magnitude less than we have in the ISM. And we don't currently have a good model for diffusion that could explain this. And well, the usual quasi-linear theory that people use to study diffusion of cosmic rays doesn't quite explain these values. So we have several authors trying to explain this. If you are interested in studying a bit more, there's this review by Feng. It goes a little bit into a little bit of detail about each of these modelings here. So yeah, okay. So so trying to explain like how we can use certain characteristics to try to explain this slower diffusion. The other approach that people usually do is just assuming a certain diffusion coefficient and try to replicate that. But usually this doesn't come with a a physical like a physical modeling. It's kind of like just fitting the data and trying to find out what we can how can we reproduce that. And usually people go to this Kolmogorov diffusion, but it doesn't take into account the proper magnetic field effects that, as we just saw, like it can be very, very important in these regions. So we've been studying another venue that is called mirror diffusion, and what is particularly exciting about this mechanism is that it's unavoidable in any MHD system. So what does it need? So first, it's in the name, the clue, the magnetic mirrors. So when we think about mirrors, we can think classically a system like this. So we will have like some kind of compression in the field lines, and the particles will spiral around, and then in this concentration they will bounce and bounce back, and they will stay there as long as they are not being accelerated in any way. So, and what is interesting is that in this process, the magnetic moment of the particle will be conserved, and this is one thing that will, as you will see, we can use to identify in the ISM, or at least in our simulations, where the mirrors are happening. And well, and then we can calculate like when these particles will be trapped by the mirrors. But this is not enough because, well, if there is only mirrors, the particles will be trapped and they will not continue to diffuse away from the source, and we need that because, well, we are observing gamma rays, we can observe cosmic rays, and etc. So we need another thing that we call the super diffusion of the magnetic fields. The idea here is that due to turbulence, the magnetic fields lines will reconnect and will change, will be affected by this movement of the gas, and we start to see something like this. So if we get a lot of lines that are close at one point, and we go along them, we start to see that they start to spread, and this process of this spreading of the lines is similar to what we see, for instance, in the atmosphere with smoke, which we call Richard diffusion. So these lines are just like spreading, and this allows for the particles to bounce around. So if you follow the red and blue lines there, so that would be like the example of two cosmic rays that start, two particles that start close to each other in the lines. So, but as they follow the lines, they will find mirrors, and they don't come back in the same line because of this effect. They end up in other lines, and then they can spread around, and this can help explain the perpendicular diffusion in this process, and why the particles do not stay trapped in the mirrors. And well, summing these two, these are some previous works studying exactly that. In the left there, you can see this process. Like we have a bunch of particles that start together, and as they follow the lines, they spread around. And in the right here, we have exactly the mirror process, that as the particle finds different bounces, comes back, but it doesn't quite come back in the same place. It bounces a little bit to the side and keeps going perpendicular to the magnetic field. So, and this is great because it helps explain one of the biggest problems in the quasi-linear theory, that is the change of direction of the particle. So if you go through the calculations, you see that when the particle starts to go to 90 degrees, there is the equations go to infinity, and you cannot explain that. Like process like this just with that. So we need some process like this. And as I said, as long as you have turbulence, magnetic fields, you have super diffusion, and due to compressions, we can have mirrors. So to test this a bit further and see how, oh sorry, forgot an R there. So it should be mirror versus scattering. So so to compare how much the scattering, so pitch angle scattering, just this process that we get from the quasi-linear theory, and how it compares to the mirror. We built a few test particle simulations, trying to compare this. So testing varying the Larmor radius, the initial pitch angle of the particle, and the background field. So this is so we have the same simulation that I showed you earlier, that we were studying the filaments. Now we are going to focus in the fields. and I did two cuts here of the lines. One of the field lines. One where we get all the structures, the entire field, and one where we cut out the small perturbations of the field. And these small perturbations are the ones that are so it would be this line here. This part of the spectrum would be the one that is more important for the quasi-linear, for the pitch angle scattering. So we are kind of reducing that and leaving only the mirrors to try to trap the particle. So what we see then? So this is a piece of the box. You can see the particle here. So as the particle starts to travel, it finds a mirror, stays there for a while, and then escapes again, and then it will re-enter the box, find another mirror, stays there again, and this process continues and slows down the particle diffusion along the field lines. And it's interesting that, well, if we follow, then we look a bit more into the pitch angle. So first line is the pitch angle evolution, so the cosine of the pitch angle actually. As you can see, here with the complete field, so where we have mirror plus scattering, there is a lot of variation in the pitch angle. You can see that as the particle travels, here in the middle is the same region of the previous slide. So you can see that the particle stays there a while and then escapes. And then after it escapes, it gets trapped again. And especially if you look here, this is the magnetic moment. You can see that it stays more or less constant during this process. When we look at this moved case, so when we remove this pitch angle scattering, we remove these fast variations, the particle is a lot more well behaved. But once it escapes from these regions, since we don't have these fast variations anymore, the particle only escapes and goes away, and it takes a long time to come back. And but you see that in this process here, it stays constant, completely constant. So we are seeing the mirror acting there, so slowing down the particle. Okay, so if you calculate then the diffusion, how much do we get there? Do we get the 10 to 28 that we need to explain these observations? And the answer is yes, actually. So we actually scaled these models to a 3 microgauss region. Would be similar to what we have around a pulsar like Geminga. And what we see is that once the particles reaches this diffusion process, it stabilizes around 10 to 27 here. But especially for the small alarm radius here, I can go into a bit more details later on if you guys want. But due to this process that I told you that the particle escapes and doesn't quite come back because there isn't a lot of pitch angle scattering, the particle actually reaches a higher diffusion coefficient, but it's still around 10 to 28, so it's still inside the range. So even if the pitch angle scattering is not present or is not too strong in the system, mirror alone could still be enough to slow down the particles and trap them around the sources and explain these diffusion coefficients. And well, here we did some calculations to scale this for a few different systems. But I want to call your attention to the green squares, where you can see above is our calculated diffusion coefficient, and if you compare with the coefficients that observations that they get from the observations, it's more or less of the same order of magnitude. So the mirror diffusion seems to explain really well these observations. So to finish this part, then we wanted to apply this to a real system to try to recover the spectral energy distribution of a source. For that, we chose W43 especially because of these simulations by Pollack, which Pollack et al. 2023 of a young massive stellar cluster. It includes several of the necessary ingredients. So it's photon fields, of the feedback from the stars. It forms a lot of the stars. The turbulence is already there, so we can use that to study the gammas that come from these regions. So we built two modelings here. To model, we don't know exactly where these cosmic rays are being accelerated in these sources. This is another problem because we don't have the resolution yet, so we're not sure exactly what is happening in there in this sense. But it could be, for instance, that we have a very compact source, let's say a pulsar in the middle of these massive clusters, or it could be that actually the total wind of the stars can form a super bubble, and this super bubble around the star, the middle of the cluster, is what is actually accelerating all these cosmic rays. So to test that, we are going to build a Monte Carlo simulation considering these two kinds of sources. And for that, so we use the CRPropa, which is a very powerful framework for testing these kind of things. We using these two modelings of the diffusion, so based on mirror diffusion. So these two dependencies, each 1/3, which in this case would be the it would be the most likely due to the characteristics of the turbulence in these regions. Each 0.7 would be if the mirror is extremely effective, and depends a little bit, but it's less likely in this scenario than the other one, but still it's a good comparison. And then we consider these different, the CMB, the photon field from the stars, the background infrared star field, photon field that comes from the stars in the galaxy, the gas, etc. And the dust of inside the system that we have from the simulation. But the dust, as you can see, the energy density of these photons is way below the other one, and in the end it won't be important, but we calculated it, and it's just not that important for this system. So what we have there, then we can expect we'll have several non-thermal processes happening, and well, we can expect, of course, synchrotron from especially from the electronic component, but these won't. This will give photons for the system there, but there are other processes we need to consider. So especially inverse Compton, as you will just see in the next slide, is one very important, and especially the interaction of photons with the hadrons, so protons present in the system, and we would have the formation of several secondary particles that will then populate the gamma rays that we observe in these regions. So here are the results then. So in the left here, these two results here are for a source at the center. So we see that in the left there, we are considering the diffusion proportional to each 1/3. So the most likely mirror plus scattering that we should have in this region. And we can reproduce this spectra with an injection of CRs close to E2-2, which would be corresponding to a Fermi-like process of acceleration. If we go to the slower diffusion, however, we actually we would need a flatter injection of cosmic rays to reproduce the same spectra, which shows us two things. This right one seems less likely, but we can actually reproduce with more than one parameter. So we have a degeneracy there that we need to go into a bit more details in the future. But well, this is problem for future me. But right now what we see is that the diffusion seems to be well explained by the each 1/3 with the injection to H-2. And one other thing is that there is different contributions between pi0 decay, so the black line here, and the inverse Compton. In this case, inverse Compton doesn't seem to be too strong, but in this case here, we would have this inversion of the contribution, especially at the smaller energies. If we compare, however, the source at the center or the source at a shell, so this here the most likely scenario that we have, you see that actually doesn't seem to show too much, doesn't have a lot of difference. We pretty much have the same behavior in both cases. So at least from the spectrum alone, at these energies, we cannot see any difference. So we might need to look at other parts of the spectra, or I don't know. We need other information, more information to understand. And well, so summarizing the results we had from the second part. So mirror diffusion inhibits this overall diffusion of CRs present in any MHD turbulent system. Can be effective even in the suppressed pitch angle scattering. And as we saw in our results, the slower diffusion laws, the CR should be obtained near the source. So these results also can be important when modeling particle acceleration. This was, for instance, showed by Bell around supernovas, which is like it is discussed how much it can accelerate or not. So yeah, like if we have mirror diffusion there, it could become like a powerful, or could help explain some of the observations. And the 3D simulations of the cascading, so these CRPropa simulations, suggested the mirror can explain this, the spectrum. But well, there are some degeneracies, especially if we look at the center or the shell. We don't, at least in this case, we cannot explain the difference between the two. But in the very near future, we have new facilities being constructed. CTAO will be the largest gamma ray observatory that we'll have in the world, and SWIGO also will be also built in Chile. SWIGO will be the counterpart in the southern hemisphere for LHAASO. And right now, we are already starting the work for CTAO using ASTRI. ASTRI already has 3 telescopes installed at Tenerife. It's already collecting data. We are already working in this data, and there are 3 working, 9 already installed, and there will be a 10th in the future that will also be installed there. And most of them are just like waiting the camera, because they are already installed, and until the end of the year they will be operational. So there is a lot of stuff to be done in these higher energies. There's a lot of new results to come in the very near future. And well, if you guys are interested in that, there are people in the institute that will here in the institute that are already working with CTAO. And that's it. So thank you very much.
Thank you very much, Lucas, for this wonderful talk. So let's open for questions. Okay, I will break the ice. I have a lot of questions, but I will start with one only. Regarding your first part of the talk, when you were discussing about your conclusions, you conclude that the gravity enhances the compression perpendicularly to the magnetic field at higher densities. What do you think would be an astrophysical impact of course, in the context of the interstellar medium of this finding?
Sorry, you mean so you mean like the compressions of the? Yes,
this conclusion that you have here.
Yeah, okay.
Like astrophysically, what would be the consequences of that, or what do you think?
Yeah, okay. So this is like there's a lot of people discussing like some modelings of how do we actually form these structures. So what we see in our models is that like these compressions come from the turbulence. So the turbulence we start compressing the lines. The lines will be a little bit enhanced by this compression. But then since you have more density there, the gravity will take over at some point, and then it starts to collapse. And then like since the field is strong enough, it will start to follow the lines because at that point, and then you start to form this perpendicular, and start to form stars, start to form this. But then once it forms there, well, we will need to go further into the resolution, because then it can start to how do you say, fracture, and then you can have this process again at a smaller scale. So it's a very complex process that goes like in several can repeat like in several scales. But like in this initial part that we have this compression will form, especially because of this compression, and then gravity will assume and start to make the matter stream along the field lines. Yeah. Yes. Along these pancake-like things, right? Yes, but then yes, but then there's a thing that there's a limit. Like there's scales that like this goes up to, because at some point that the field can kind of break down. It doesn't go. It can twist. Like there are some results that like once the stars form, they do not necessarily all follow the field line that was around them. So it's a bit more complex when you go to smaller scales. But still, the initial process of star formation starts with this collapse, this big collapse of the.
You mean smaller scales, like the scales of the protostar?
Like other process can kind of like twist the field around, so you may lose a bit of the information. So not all the stars will end up there, but because you have other things happen, you can have feedback, and so of course. I'm just saying like, okay, like it's not. This is. I'm just calling attention that it's not that the field will be the same all the way to the star, but like still like the initial there, it will be the field will be the main. Yeah.
I get. Yeah. Okay. Thank you. I have one question.
Hi, Lucas. With regard to the polarization that you showed, I think that from your simulations you calculate directly the Stokes parameters, and when comparing to the observations, the authors probably use like the Davis Chandrasekhar Fermi method that assumes the frozen condition of the magnetic field along the fluid of the interstellar gas. In your simulation, like, even though I think you do not have explicitly resistivity, but you can, in ideal MHD, have the numerical resistivity, you can have like magnetic reconnection that violates the frozen condition of the plasma. So do you have any counterpart of the magnetic reconnection in your polarization calculations? And
yeah, no, in this case here, we did just a simple assumption of the gas there being emitted by the light being emitted by the dust. So just as if it was just like thermal emission of the dust. And then the thing is like we didn't even like did any assumption of depolarization, which is something that happens, because like, for instance, just dust alone doesn't will not be fully aligned in a real environment. So we should even consider that. So this is like a simple assumption to see like the best scenarios. And also, I don't think we may see like some kind of reconnection in the simulation, because like it's a numerical method. But yeah, our resolution and our scaling wouldn't be like a good representative of these kind of effects. So
yeah. By the way, what is the resolution that you used in
the
that?
higher like these ones are 512 with gravity. Turbulence only were just 256. But yeah, so.
Okay, thank you.
Yes. Yeah, regarding what we see in the interstellar median, it is actually like yeah, like these resolutions, like if we calculate the spatial resolution of our simulations, it's still way better than whatever observation we get from Planck. Yeah. So we still have like if anyone is interested, there is we did like a small estimation for Musca in our paper, and actually like there's some problems. There could be like some inversions of the results if we don't, depending on the region, if it doesn't have enough resolution. So yeah, like at least for the testing to understand this, our resolution is good enough to understand the polarization, to see how this is working with the filaments. But when you consider the real data, yeah, like there are more problems.
But nevertheless, you can use the same technique to search for reconnection in places where reconnection is important.
Yeah. Okay. Yes.
It's the same thing. Just that in those regions, it's not that these are, large scale turbulent regions of the interstellar medium, where you cannot catch specific regions where reconnection there is important, right? It's different when you are in the surroundings of a compact source, for instance.
Yeah. 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 So. Yeah, that's it. Like, we could use I don't know if you guys heard, like, that's just the comment that we could use these techniques to, like, around like more compact regions to try to trace this. But yeah, not quite the case here. But it's still like it is possible.
Great, thanks.
Okay, more questions? Okay, I will ask another question regarding your modeling at gamma rays of the W43 cluster. And you found that there is a degeneracy in one of your results, that you cannot distinguish between the two. I will wait until you get the...
Yeah, like this one, for instance.
Yeah, here.
In the center in the show.
And you also mentioned the next generation of gamma ray facilities, right?
Yeah.
I wonder if you think what would be the ideal conditions of or an ideal observation that would break the degeneracy of your model?
I don't know. Maybe if especially in the case of the W43, maybe the like okay. So okay, in the case, for instance, of W43, we could have like this degeneracy between being outside or inside. So I don't know, maybe if the observation can resolve between the two, like let's say we can find like a kind of a shell emission around and not like a central, something like more central, maybe this could help then like see which one. But like here we are pretty much using like 4 parameters. So the diffusion coefficient, the any energy injection dependence, and the eta of the how efficient is the injection, and then this region where they are being injected, right? So yeah, I don't know, like if we can get like more information about these, maybe we can also somehow we can get like more information about the energy injection we are getting there, or maybe the actual efficiency of this process. I don't know. Maybe it could help us break this somehow.
I see. Oh, after I have another question for Lucas. Yeah, but
CTAO and SEMINÁRIO will remove this diffusion.
Yeah, they will have yeah, but they will have the resolution to look into
like
this.
Exactly what would be the
I would I think that for instance in these sources, for instance, the CTAO and ASTRI will probably have the resolution to look like closer, and maybe instead of seeing this big blob that's bigger than the moon, we'll be able to see like more detailed where the emission is coming from.
But do you calculate that would be able to? Or
I'm trusting the results I remember from from previous CTA meetings, but
it's fine. I'm also curious before I give you the microphone, because I am curious about what is this black line here.
So sorry, it's in the previous slides because so the black line is it what comes from pi 0, so coming from the hadronic chain. So from PP, so PP will the 2 protons interact. it will produce some things. It will form a pi zero along the line. This pi zero will decay into gamma ray. So this black line is the one coming from these pi zeros that are formed from the PP interactions, and the red one comes from the inverse Compton. And the inverse Compton, most of the electrons also come from this PP interaction. It will form a pi plus or pi minus, and it will also decay into an electron positron.
I see. Okay.
So and then this will also be able to. Yeah, second. It will also lead to a to a gamma ray emission.
Additional.
Yeah. So the. Okay. So PP it will. So pi plus would get these positrons, electrons, and then there is not the pi zero. No, there is the pi zero here. Pi zero will also decay.
Okay.
I just wanted to ask. No, I don't remember which comment. No, the comment was just that of course LHAASO was unable to localize the source immersed in this cluster, supermassive cluster, right? Yeah. So I think with the with CTAO and Astronomia array, we are going to have the means, the resolution enough to say whether the source is a microquasar or a pulsar wind nebula embedded in the cluster, or the entire contribution from the winds, the super bubble wind from the massive stars, right? Which is kind of possibility, probably more probable that this is the case. Yeah, of course. Yeah.
It's just that I wanted to, before I forget the line. Okay, so more questions? Great.
I think it was slide 55. Also in the SED. I might have missed it, but what is the solid black line?
This one?
Yeah.
Oh, sorry. This one is the cosmic rays leaving the source. So this, so this is something that I forgot to comment, but yeah, like this is something that also maybe if we have some information around the source, it could maybe help explain which modeling could be having there. Because, for instance, in this case here, we do have the cosmic rays leaving all the way down to 10 to 10 electron volts. But if the diffusion is low enough, these cosmic rays will be absorbed inside the source, and only the highest energies will be leaving. So if somehow we also can like estimate these cosmic rays, like there's some information of what is leaving the surroundings of these sources, maybe could help us identify which diffusion regime we actually have inside this. And this, like this, for instance, for the shell modeling, they usually assume very slow or a very slow regime, like sometimes usually like E2.7 or even E2.1. And so then we wouldn't see this. It should maybe be something like this for the cosmic rays leaving this shell. So and then maybe the surroundings will contain some information of this. So could be a way of differentiating what we have.
Thank you.
Yes, you're right. You have like and it goes to my more questions. I promise my last question because it's related to what you are mentioning and with the slide that you were showing. When you compare your findings of the diffusion coefficient, compare with the observations in the TIV halos, you give a number of the diffusion coefficient, but it depends on the energy. What's the energy that you're talking about?
Sorry, it's all around like 0.1 PeV up to 5, almost 4.5 PeVs, depending on the modeling of the magnetic field, and the size of the region we scale the model. So we can play around a little bit with these values over here to get like different scalings for different magnetic fields and size of the system, and these will have like a correspondence in the energy, and then we can calculate the diffusion coefficient from what we obtained from our models. So yeah, so this I got from the so these values here are like for the energies around 1 PeV, which is more or less what we would we want to explain in these regions? So like how long does these very high energy particles stay there? So
I see. Yeah, that would be the highest energies that you need for the particles to produce the gamma rays you observe.
So yeah, like above. So for the observations that we have right now, we need something from 1 PeV above. So that's why we are searching for the PeVatrons, because like these sources would be the like up to 10 to 17, and they will be the correspondence to these gammas that we observe with LHAASO, future with CTAO, so ASTRI. So yes.
I see.
Betty.
I have a comment, a final comment that actually Lucas forgot to say, that one of the main results of this work, actually I think it's the most important one, is the fact that we have for the first time a physical motivation for the diffusion coefficient being proportional to the energy of the cosmic ray to the power of 1/3. Because this power 1/3 is generally assumed in literature, in some cases just like a guess, based on Kolmogorov turbulence. But there is no physical basis on this choice. And then they simply compare, 1/3, then they try another one and another one. And here, for the first time, we have a physical meaning for this 1/3, that is, cosmic ray diffusion is due to both the particle pitch angle scattering, because it's unavoidable, the particles will scatter anyways. Quasi-linear theory predicts this, but this composed with mirror diffusion. So scattering plus mirror diffusion provides this dependence on the diffusion coefficient of the cosmic rays in any turbulent environment, either in interstellar medium, intergalactic medium, or in the surroundings of a source, like the accretion flow around the black hole. Any turbulent system, this should be the physical motivation, this dependence to the power E to 1/3, because these two processes are present, and are unavoidable, because if you have MAGD turbulence, right? So it's scattering plus mirror diffusion. And I think this is the point. And this will remove degeneracy in the studies, in the theoretical and the observations as well, to explain. And then you constrain the diffusion coefficient and obtain values that are comparable to observations, which is nice, right?
Yeah, of course. That's what we want.
This is
compare with observations. Great. Okay, more comments? No? Thanks, Lucas, again. Thank you very much, Lucas.
Thank you so much.
And let's continue the discussion in the coffee break.